Hello everyone, I'm Jyoti from BSc Chemistry Honors second year. So this video is specially for visual impaired students and the chapter name is Chemistry of Lanthanide Elements from Inorganic Chemistry. Let's start. Lanthanides are the elements present in period 6 of the periodic table with the atomic number 57 to 71. Since the last electron in the atoms of these elements enters the 4f orbital, therefore these elements constitute what is known as f-block elements. These elements are also named as inner transition elements. This is because these elements constitute our transition series within the third transition series, more precisely the 5D transition series. These elements are located in first row of elements kept at the base of the periodic table. The first element of the series is named lanthanum, and a group of 14 elements following lanthanum is called lanthanides. In other words, elements starting from cesium and ending with lutetium are known as lanthanides. The name lanthanides was wrongly assigned as the ending "ide" more correctly means a negative ion such as oxide or chloride ion. For few years, Epic suggested a new name, lanthanons, instead of lanthanides to these elements. However, it was also disproved soon because the ending on is preferred for non-metals, whereas the lanthanides are all typically metal elements. IPEC has finally approved these elements to be named as lanthanides with the ending "oid." These elements in the earlier years were called rare earth elements because of their occurrence in very small amounts. However, nowadays the term rare earth element is itself misleading because many of these elements have been found to be abundantly available. For example, cerium is as abundantly available as copper. Huge deposits of these elements have been located in USA, USSR, Scandinavia, and India. Electronic structure and position of lanthanides in the periodic table. As already discussed, lanthanides involve the gradual filling of 4f orbitals. The ground state electronic configuration of each lanthanide is occupied by the outermost shell of by the two 6s electrons. Since the energies are similar to the order of filling of the 4f orbitals may show some irregularities. It is found that at lanthanum the incoming electron enters the 5D subshell and therefore it has the following electronic configuration as given below. Here are the name of the elements, that is lanthanum, cerium, praseodymium, neodymium, bromadium, samarium, europium, gadolinium, terbium, dysprasium, holmium, erbium, thulium, ytterbium, lutetium. Physical constants of lanthanides. Some of the important physical constants of lanthanides are given in table. As ionization energies, lanthanides have low ionization energy. Final energy of the lanthanides increase in general but will show little variation with lanthanide series. The trend is less clear for the first ionization energy than for the sum is clear from the deviations are observed only for europium, gadolinium, and ytterbium and lutetium filled and completely filled f orbitals, half filled and completely filled half f orbitals. Melting in boiling points. The melting point uh, of any substance reflects the forces of attraction between the atoms, molecules, or the ions. The composite solid and inspection of the table reveals that lanthanides possess high melting and boiling points. However, the melting and especially the boiling points of lanthanides do not show any regular trend across the lanthanide series. The properties of the lanthanide strongly suggest that these valence electrons per atom are involved in the metallic bond. The 4f electrons are not involved in metallic bonding as these are located on the individual atoms and are well shielded from each other. The most clear-cut anomalies in the lanthanides are probably the europium and terbium, which behave much as would be expected of divalent metals, including 3 electrons per atom involved in metallic bonding. These are also the two lanthanides which more from divalent ions in their compounds. In addition, these two ions have half-filled and completely filled shell respectively. This explains low melting points in case of europium and terbium as compared to the value for the other lanthanide elements. Density. The densities of the lanthanides do not display a regular trend across the lanthanide series. Both europium and ytterbium have unusually low densities. Heat of fusion and heat of vaporization. The amount of heat required to convert a substance solid its into melting point to a liquid is called heat of fusion, whereas the amount of heat required to convert substance from a liquid into its boiling point to a gas is called a heat of vaporization. Both the energy required is used to overcome the attractive forces. In case of lanthanides, the heat of fusion and heat of vaporization do not show a regular trend across the lanthanide series. Electronegativity values. Pauling defined electronegativity as the power of an atom to attract electron towards itself. The length and show the lower Pauling electronegativity values. Since electronegative values of length is almost same as that of s block elements, anticipated that lanthanides from any compounds. Oxidation state of plus 3 shown by all these elements, and in most cases is the most stable state. Some of the lanthanides in addition to plus 3 and plus 2 and plus 4 oxidation state. However, plus 4 oxidation state are always less stable than plus 3 state. The reason for the unusual oxidation plus 2 and plus 4 can be attributed to the extra stability. Plus 3 oxidation state: lanthanum, gadolinium, lutetium, uh, and the Shaw's plus the oxidation state is because after the loss of three hydrogen electron, these elements for stable electronic configuration. Plus 4 oxidation state is required by terbium and cerium, etc. Plus 2 oxidation state is required by terbium and ytterbium. Magnetic properties. The magnetic properties in chemical compounds determine the presence of paired or unpaired electrons. If substances containing only spin paired electrons are placed in the magnetic field, those are weakly repelled by the field. This phenomenon is called magnetism. On the other hand, substances containing one or more unpaired electrons, when placed in the magnetic field, are attracted by the magnetic field. This phenomenon is called paramagnetism. It is important to note that the attraction of each unpaired electron is many times stronger than the repulsion of all the spin paired electrons in that atom. Most of the lanthanide ions, with the exception ions, are paramagnetic. The paramagnetism in the lanthanide ions arises because of the presence of unpaired electrons in their 4s shell. The magnetic behavior of substances is expressed in terms of magnetic moment. The larger the number of unpaired electrons, the higher the magnetic moment. The magnetic moment arises from two types of motion of the electrons. The spinning of electrons on its own axis generates a magnetic moment called spin magnetic moment. Orbital motion of the electron around the nucleus also produces magnetic moment called orbital magnetic moment. Both spin magnetic moment as well as orbital magnetic behavior is behavior of lanthanides in with the behavior of transition elements d block, where the magnetic moment corresponding excluding spin only values. In case of transition elements, the d orbitals are not well shielded from the environment, attract strongly with the ligand surrounding the metal, and because of the electric field of the ligands, orbital motion of the electron is restricted. That causes the orbital moment to decrease considerably. In other words, the orbital moment of the electrons in case of transition elements can be neglected. On the other hand, in case of F-block elements, the 4f subshells are well shielded from the surroundings as interact with the surrounding ligands. As a result, orbital motion of 4f orbitals is not influenced. The theoretical and experimental determined magnetic moment values of the tripositive lanthanide ions are given in below. All the tripositive lanthanide ions excepting and 3 positive value 3 positive contain unpaired electrons are therefore paramagnetic. A plot of magnetic values tripositive lanthanide ion reveal the magnetic moment values increase up to niobium and then decreases up to samarium. It increases steadily again, reaches a maximum value for dysprosium and then start decreasing till this zero value for lutetium ion, which is diamagnetic. It is important to remark that high values of magnetic moments clearly demonstrate the role of orbital contribution towards the magnetic moments of electrons. Color and spectral properties. Lanthanides in their elemental state are silvery white, while many lanthanide ions are distinctly colored both in the solid state as well as in the aqueous solution. The color of the lanthanide ion depends properly on the number of unpaired F electrons. The color of the lanthanide ion remains same even on changing the counter ion. The color of the lanthanide ion is characteristic of the cation. It has been found that the lanthanide ion containing NF electrons often have similar or color to those of with 14 minus NF electron. The color of lanthanide ions can be grouped symmetrically about the trivalent gadolinium as shown in table. The color of the lanthanide ion due to primarily to the absorption of light from the visible region of the spectrum that results in the electronic transition while the 4f level. This type of transition is called FF transition. A unique feature of the spectrum of tripositive lanthanide ion is that the absorption bands are sharp line like bands in the ultraviolet visible near infrared regions. This behavior is in contrast to absorption bands of DT type transition metals, which appear as broad absorption bands. The hands of lanthanides ions are so sharp that they are used for characterizing lanthanides. The reason for every sharp absorption and bond is the 4f orbitals are located deep inside the atom. Thus, they are effectively shielded from environment factors such as the nature and number of ligands, which form the complexes and form vibrations of the ligands. It is important to mention here that the behavior it is contrast with transition elements where the transition give absorption bands whose position changes from ligand to and width of the peak is greatly broadened because of the vibrations of the ligands. However, lanthanides in the plus 2 and plus 4 oxidation state with the same number of electrons do not have the same color as observed in case of lanthanides in plus 3 oxidation state. Some of the typical isoelectronic lanthanides in plus 2 and plus 4 are shown in table. Uh, Ionic radii and lanthanide contraction. Covalent and ionic radii increase or moving down a group in the periodic table. This is due to presence of additional shells between successive periods. On the other hand, moving from left to right across a period, the covalent and ionic radii decreases. This is attributed the increased effective nuclear charge as a consequence of which of the outermost elements are attracted more and more. This results in outermost electrons being pulled more and more closer. We also know that the shielding effect of electrons decreases in order SPDF. The atomic and ionic radii of lanthanides are given below. Uh, a careful inspection of the table reveals that as we move along the lanthanide series from lanthanum to lutetium, there is a gradual decrease in the size of the atoms and ions with the increase in atomic number. It has been observed that in case of positive lanthanide ions from C3 positive, the ion radii decreases from 1.03 angstrom to 0.86 angstrom. This shows that the overall decrease of 0.17 angstrom occurs in going from C3 positive to Lu3 positive ion. The small steady decrease in atomic or ionic radii of the lanthanide elements with increase in atomic number is called lanthanide contraction. The shapes of the orbital account for the relative atomic radii of a block element. The lanthanides involve the gradual filling of 4f orbitals. The lobes of the 4f orbitals occupy markedly different regions of spaces and are therefore far apart from each other. Consequently, f orbitals repel one another very weakly. Secondly, electron density in f orbital is low near the nucleus. As a result of being away from the nucleus, 4f orbitals are not very effective at shielding other electrons from the nucleus. This contraction in the size of atom or ion by pulling the valence electrons inward due to high nuclear charge and the poor shielding effect of the f electron is the main cause of what is called lanthanide contraction. Consequences of lanthanide contraction are steady decrease in size of lanthanide ions, electronegativity, electrode potential, resemblance of second and third transition series. There is in brief, as a result of lanthanide contraction, the chemistry of second and third transition series resemble each other more than the remains of first and second transition series. Difficult in separation, high density, difference in basicity. Because of that, only OS3 is the strongest, while LuOS3 is the weakest base. Difference in basis is related to hydrolysis of ions, solubility of the acids, and the thermal decomposition of oxysalts, complex formation tendency of lanthanides. Compared to the transition metal, lanthanide do not readily form complexes. It is similarly due to the large size of the ions, which result in the small charge to ionic radii ratio. Lanthanide ions form complexes preferably with fluorine and oxygen donor ligands. They form complexes with beta diketones such as acetylacetone oximes, ethyl acetic acid, and hydroxycarboxylic acids, as given below. The lanthanide elements are often six coordinated in complexes. The higher charge density of CF4 negative is expected to form stronger complexes than the Tripositive in CF4 positive has been found to form the dianionic complex in non-aqueous medium N2O4. This is interesting complex in which the coordination number of cerium is 12. Nitrate ion behaves by identical shown. Organometallic compounds, lanthanide ions being highly electronegative positive, do not form complexes with pi bond ligands. The inability to form complexes is also due to non-availability of f orbitals for bonding. However, lanthanides form two types of compounds. First are predominantly ionic cyclopentadienides, alpha bonded alkyl aryls. Occurrence of lanthanides. Lanthanides are originally named as rare earth or rare earth metals um, elements because they were believed to be rare. However, the term earth is misleading as they are actually fairly common now. The word earth was used because most of these elements occur as oxides with the exception of Promedium. All the lanthanides occur naturally. Recent studies have revealed that some of the lanthanides, cerium, lanthanum, occur in fairly abundant quantities. It has been found that lanthanides with odd atomic number are less abundant than the lanthanide with even number. A number of minerals containing lanthanides are also some of the important minerals are that is moissanite and Westernite extraction of lanthanide from monazite. The mineral is crushed to obtain fine powder. It is digested with concentrated sulfuric acid till a paste of lanthanide sulfates is obtained. The paste is separated by centrifugation and treated with cold water. When silica being insoluble is separated out, the solution containing soluble sulfates is neutralized with ammonium hydroxide. When thorium, zirconium, and titanium are precipitated as the respective phosphates, the precipitated double sulfates of heavy elements are treated with a concentrated solution of sodium hydroxide. Methods of separation and individual components. The properties of metal ions are governed by the size and charge of the ions. Since all lanthanide ions are nearly the same size and inherently carry positive charge, they have almost similar properties. As a result, the separation of lanthanide from the another is extremely difficult. A number of methods have recently been developed based upon the repeated fractional crystallization, precipitation, ion exchange methods, etc. Second point, then precipitation. With the small amount of precipitating agent, a substance with the lowest solubility is precipitated over force. Suppose hydroxyl ions OH negative are added to solution containing a mixture of lanthanide nitrates. The weak base which has the lowest solubility product is precipitated first, and the stronger base which has the highest solubility product is precipitated last. The process, when repeated several times, helps is the complete separation of lanthanides. Solvent extraction. This method of separation is based upon the fact that the solubility of lanthanide and organic solvents like tributyl phosphates is different in the solvent extraction process. Um, Nitric acid solution of the lanthanide is exactly extracted by means of a counterflowing solution of tributyl phosphate in kerosene. Complex formation complex agent like ethyl diamine, tetraacetic acid are well known to form complexes with lanthanide ions. The stability of these complexes increases with the decreasing size of the lanthanide ion. Thus, lutetium lu 3 positive complex EDTA is the most stable of all the complexes of the lanthanides with the EDTA some acid to the solution. These complexes the less stable EDTA. Change in oxidation state. Most of the lanthanides exhibit an oxidation state of +3 in its compounds, whereas a few lanthanides show the oxidation state +2 +4 as in its compounds. As a result, lanthanides with plus oxidation state have um, properties altogether different from lanthanides with +2 +4 oxidation state. This is different in the properties. Different oxidation states is extremely useful in the separation of lanthanides. In exchange method, uh, ion exchange method. Ion exchange method is one of the most convenient and efficient methods for the separation purification of the lanthanides. In the method, a solution of the lanthanide ions pass through a column of synthetic ion exchange resin which contains the functional group lanthanide ion when come in contact with the resin containing the acidic functional group undergo proton exchange. Since lanthanide ions are present in aqueous solution, these are heavily hydrated lanthanide ion. In the most heavily hydrated is the lutetium, which is most heavily hydrated, and it means the size of hydrated lutetium is maximum size hydrated lanthanide and binds strongly with the resin and all size lanthanide the resin. Resin. Production of lanthanide elements. We have listed in the preceding section a number of methods for the separation of the lanthanides. In this section, we shall list method of production of elements. Electrolysis of fused chlorides. The mixture of lanthanide chlorides LaCl and is electrolyzed in a graphite line steel cell which serves as the cathode and graph process is mainly used for lighter low melting C and for some in European samarium reduction of anhydrous chloride with solution lighter lanthanides such as by the reduction of the corresponding chlorides with element of sodium at 1000 degrees Celsius. Reduction of anhydrous trifluorides with calcium magnesium. Compounds of lanthanides. All the lanthanides are soft and silvery white metals. They are highly electropositive and therefore very reactive. The heavier lanthanides are less reactive than the lighter lanthanides because they form a protective layer oxide on the surface. Most of the lanthanide form compounds in plus 3 oxidation state. However, some compounds of lanthanide plus 2 plus 4 oxidation state. Compounds in plus 3 oxidation state all the lanthanum metals turn steadily in this bond in oxygen, forming the corresponding Na2O3. The oxides can also be prepared conventionally, either by heating the carbonates or by decomposing the corresponding nitrates. Na2O3 is a strongly basic, whereas Lu2O3 is weakly base. Lanthanide hydrides are given below. Lanthanide halides, lanthanide nitrides, oxalates of lanthanides. A large number of oxalates of lanthanides are known. These include nitrates, carbohydrates, oxalates, phosphates, and perchlorate. These are generally prepared by dissolving the hydroxide or carbonate in the corresponding acid. Double salts of lanthanides. It is important to note that the lanthanide sulfates are known to form double salts, NH4 bases of Lu2, SO4 thrice, and H2O. However, the double salts of lanthanides cannot afford to associate it with as many as 24 water molecules of crystallization. This is because the lanthanide ions are wrong too big to coordinate to for 24 to 4 water molecules of crystallization of title in alum. Inspection of plus 4 3 oxidation state is shown by lanthanide namely samarium, europium, ammonium, europium and terbium display the plus 2 oxidation state by acquiring the stable F electronic configuration. Equivalent compounds EuCl2 can be prepared by a solid compound by reducing MEuCl3 with gaseous hydrogen under pressure. Um, Aqueous Cu3 positive solutions can be reduced by a variety of reducing agents such as MgZ and zinc amalgam, uh, or electrolytically give U2 positive. The dihalides are also prepared more conventionally by the reduction of the trihalides with lanthanide metal itself, as Cl2 have been prepared in quantitative yield by reacting the metal with 1,2-diethane in anhydrous THF. Lanthanide compounds and 4 oxidation state are an inspection of or reveals that CEP or NDTP and DY show the plus 4 oxidation states among the lanthanides. The only plus 4 oxidation state have is stable in solution and has rich aqueous chemistry in cerium compounds that are extensively used as versatile oxidizing agent in quantitative analysis. The stable iodides of samarium, europium, and deuterium can be prepared by the thermal decomposition of their triiodides, as praseodymium fluoride can be prepared indirectly by fluorating a mixture of NaF and PrF3 with elemental fluorine, which gives Na2PrF6. Extraction of NaF and Na2PrF6 with liquid HF gives PTF4. Neodymium fluoride is known only as a double salt C5,3NDF7, which is formed by the fluorination of mixture of CaCl and NaCl3. Some of the important reactions of lanthanides are summarized in the box. Thanks for watching.